Next time you walk into a dark room and turn on a light, take a second to trace it backward. That energy travels through the wall, out to the street, and all the way back to a power plant. This diagram shows how that journey works. The grid operates in 3 distinct stages. First, power is created during the generation phase. Then, it's pushed onto massive towers for high-voltage transmission. Finally, lower voltage distribution lines carry it right into your neighborhood. But there is a catch to this system. If you turn on a water faucet, you're pulling from a tank that already holds millions of gallons. Electricity doesn't work like that. The grid cannot store large amounts of power. It is an active, live system. That means the exact moment your finger flips that light switch, somewhere miles away, a physical turbine has to spin just a tiny bit harder to generate that precise amount of energy instantly. Now picture millions of people coming home from work. They are turning on ovens, air conditioners, and televisions at entirely random, unpredictable times. The power being pushed into the wires must perfectly match the power being pulled out, every single millisecond. If supply and demand fall out of sync, the entire system crashes. So how do engineers keep a chaotic system like this balanced? To manage this, engineers rely on a virtual clone of the entire physical grid, living entirely inside a computer. They translate the real world into a network of points and paths. Every power station and neighborhood is represented by a single point on a map, all tied together by the wires in between. To make this virtual grid actually function, they use a tool called power flow analysis. You can think of it as the physics engine of a video game, making sure the digital world obeys the rules of the real world. This animation shows exactly what that math is doing. It tracks how hard the electricity is pushing through the wires and how crowded those lines are getting at every single point in the network. These equations run continuously. They provide a live, beating heart for the digital simulation, mimicking the exact state of the real grid outside. By solving these complex equations, engineers take an invisible, highly dangerous web of energy and turn it into a clear map they can safely manage. This virtual model is also how they prepare for the worst. Let's say a massive storm is rolling in, threatening a major transmission line. This digital map simulates a lightning strike, completely knocking out a main line. The analysis instantly recalculates the new paths the electricity must take. As energy detours into smaller local lines, one specific route flashes red. It's taking on too much traffic. In the real world, that red line means a physical wire is overheating. It would melt, snap, and potentially trigger a cascading blackout across the entire city. But because engineers see this happen in the digital twin first, they can fix it before the storm ever hits. They can start up a backup generator on the other side of the city to reroute the power and relieve the pressure. By pushing the digital model to its breaking point, engineers ensure the real physical grid stays standing. When the real storm finally arrives, the city stays safely lit. The emergency was solved hours before it even started. Power flow analysis also lets us look years into the future. Before we plug thousands of new solar panels or wind turbines into the network, we test them in the simulation to see how the system will react. We can run endless scenarios, tweaking the math until we design a grid resilient enough to handle our energy needs for decades to come. So the next time you plug in your phone or boot up a gaming console, think about the incredible journey that electricity took to reach you. The power flowing into your home is guided by millions of invisible calculations every single second. Math is the unseen safety net keeping our modern world running.